Okay, so college algebra, we're talking about introductions to polynomial functions. These are what we call the higher degreed equations. So we're going to start off by just talking about what the degree of a polynomial is. So the preview is determine the degree of the polynomial. So when you talk about the degree of the polynomial, you look at the x variable and the biggest exponent. So if they're written in descending order, your first term should have x to the highest power. So this first example has a degree of 4. I'm just going to put a DEG, but the first example is a 4th degree polynomial, or it has a degree of 4. Part B, you have an x to the 7th power, so this function is a degree of 7, a 7th degree polynomial. Part C, this thing is already factored, but really what you have here is approximately a negative 2, and then you have an x being to the 5th power, and then you have another x to the cubed power. So really what you have is a negative 2, x to the 5th times x cubed, which is going to be x to the 8th, and there's going to be a whole bunch of terms beside it. So if you look at the x to the 5th and the x cubed, you multiply them, you get x to the 8th. This is a degree of 8. So if you actually did all of that multiplication, your first term would be negative 2x to the 8th power, which would be your highest exponent on the x variable. So anyone want to take a guess on part D, what you think the degree of that polynomial is? 5th. So you kind of say x cubed times x squared would be x to the 5th. It is a 5th degree polynomial. Now
Don't you add them?
You add those exponents. When you multiply, you add the exponents. So now the other thing you need to take note of is that example A and example C, the degree is an even number. So it's called an even degreed polynomial. It's because the degree is an even number. So those are even degreed polynomials. Whereas B and D, their degrees are odd numbers, or odd degreed polynomials, which is going to take us into now the end behavior of even degreed polynomials. So remember, an even degreed polynomial would be something like either an x squared, or an x to the 4th, or an x to the 6th. The highest exponent is an even number. So let's take a look at just the graph of x squared and kind of discuss what it looks like. Okay, we've talked about the x squared function a lot. Okay, so that should come quite naturally to you. And what we're going to talk about now is what they call the end behavior. On the left end of the graph, it is going up. And on the right side of the graph, it is also going up. So we say the end behavior of this graph, and I'm just going to put end BEH, we say the end behavior is up, up, which means it's up on the left and up on the right. That's y equaling x squared. Now if I were to do, say, y equaling x to the 4th, the next even degreed polynomial, it looks almost identical to x squared, but it's going to flatten out a little more close to the origin or close to the vertex. So it kind of stays low, close to the vertex. And so as you can see, on the left and on the right, you're going up on the left, you're up on the left side, and you're up on the right side. So its end behavior continues to be up, up. And it's really that simple a notation, an arrow and an arrow. And then if I went to the next one, which we say y equaling x to the 6th, it really looks the same, but it flattens out even more down at the origin, a little more dramatic. So all of these even degreed polynomials look a lot alike. Now when you start putting additional terms in there, it's going to vary. But the end on an even degreed polynomial is going to be up on the left and up on the right. So the end behavior for an even degreed polynomial is going to be up, up. Up on the left and up on the right. Now I'm going to change my pen color and I'm going to stay on this same graph. Okay, but now I'm going to look at y equaling a negative x squared. That's still an even degreed polynomial, but when it's negative, what does it do to the graph? Flips it over the x-axis. It reflects it over the x-axis. So if I reflect it, what is my end behavior whenever I put the negative in front? down, down, down on the left and down on the right. And the same would be true if I put a negative in front of my x to the fourth, reflecting it over the x-axis, it would reverse or flip my end behavior so that it too is down, down. So even degreed polynomials, if they're positive, they're going to have an end behavior of up, up. But if they're negative in the leading coefficient, the end behavior will go down, down, because that is a reflection over the x-axis. So that's your even degreed polynomials. Your next title is the odd degreed polynomials. So this would be something like y equaling x cubed, or y equaling x to the fifth, or x to the seventh, or x to the ninth. That's your odd degree polynomial. So let's start at the basic one that we know, which is the y equaling x cubed. We know the graph of y equaling x cubed. And what is the end behavior of the y equaling x cubed graph? What's it doing on the left side? Down on the left and up on the right. So its end behavior is opposite direction. All of your odd degreed polynomials, the end behavior will be opposite direction on the two ends. Now, if I were to try x to the fifth, it would be very similar, except it would, just like with the evens, it's going to flatten out a little more. It will never be completely constant. It will never be horizontal, but it will just be slower in its increase as it's close to the vertex. So what is the end behavior on x to the fifth? Same thing, down on the left and up on the right. And it'll keep doing this. So if you try y equaling x to the seventh, it's going to look very similar. I'm being really dramatic in my graphs. And its end behavior will again be down on the left and up on the right. So it's an odd degree polynomial. The end behavior will be going opposite directions. Okay, opposite directions. So now I'm going to change pen color. And I'm going to change the graph a little bit. And if I change it now so that it says y equals a negative x cubed, which is going to cause a reflection over the x-axis, what is it going to do to the end behavior? What's it on the left side? Up on the left and down on the right. Same thing if I reflect the x to the fifth by putting a negative as its leading coefficient. It will have an end behavior of up on the left and down on the right. I didn't get it graphed. So I think that you can see the patterns. So if it's an odd degree polynomial, visualize in your mind the x cubed graph. Don't memorize the end behavior. Go back to the fact that you already have memorized the graph of x cubed so that you can get the end behavior right. And when you're asked the end behavior on an even degree polynomial, visualize the x squared because you know it by heart. And then if you have to put a negative in front, flip it knowing that that is a reflection over the x-axis. So use just logic. Don't memorize these arrows. Logically understand it so you don't forget it. So now let's take a look at this list of functions. We have no clue what their graph looks like, but we're going to discuss the end behavior. So on the first part A, what is the degree? I don't know how I'm getting a red pen. What is the degree of this part A? What is the degree of this f of x? It's a fifth degree polynomial, right? Because the x to the fifth, the 5 is the highest. So it's an odd degree polynomial. If it's a positive odd degree polynomial, what is its end behavior? Think of x cubed. All of them that are odd will have the end behavior of the x cubed function. What's its end behavior? Down and then up. Okay, look at part B. What is the degree of the f of x equal x to the fourth minus 3x cubed plus 5? What is its degree? A fourth degree polynomial. It's a positive fourth degree polynomial. So what is its end behavior? Think of x squared. Up, up. Just like x squared. It's an even degree polynomial. Part C. This is, good grief, this is 11th degree polynomial. So it's odd. So think about x cubed. But it's not just an 11th degree, it's also a negative. So think of the x cubed reflected over the x-axis. What is its in behavior? Up and down. Okay, think of x cubed reflected over the x-axis. Okay, the next example, what is the degree on part D? 12. That's a big old even degreed polynomial, but it's a negative even degreed polynomial. So think of x squared being your even degree polynomial reflected over the x-axis will have an in behavior of down, down. Okay, so now E, F, and G, these are in factored form. Okay, so you've got to get the degree right. On part E, what is the degree of that polynomial? Fourth degree polynomial, because remember there's an assumed 1 on the x minus 5, so the 1 added to the 3 is a fourth degree polynomial. It is a negative fourth degree polynomial. So what is its in behavior? Down, down. Part F, what is its degree? Eighth degree polynomial. It is positive, so what is its in behavior? Up, up. See, y'all got this. This is stuff you've memorized this quickly. And on the last example, what is the degree? That's the degree is the exponents. Fourth degree polynomial. It's a negative fourth degree, so the in behavior is down, down. Okay, so don't memorize the arrows. Memorize even being x squared and odd being x cubed, and you'll get that correct. Okay. All right, let's see what's on the next page. So now we're talking about zeros and multiplicity of zeros. So don't forget, you have to remember a zero is a new word for an x-intercept. And I've seen with this author him sometimes calling it a solution. Now I don't talk about it that way, but I've seen him say that. All right, so be careful when he does that. He's still talking about x-intercepts. So identifying the x-intercepts of a function. So in part A, it says, what are the zeros of this function, which means what are the x-intercepts? Well, remember the x-intercepts occur when the y value is 0. So if I take it out of function notation, and I replace now the y value with 0, I need to find the x values that cause that result. Okay, it's probably been a while since y'all have done this, but what you have to do is you have to factor this thing. And so you get an x and an x. You think of two numbers that multiply to be a negative 15 and add to be a negative 2, which is a 3 and 5 combination. Your 5 is going to have to be negative, and your 3 will be positive. Then what do? It's called the zero factor property. You said each one of these equal to 0, right? And I'm running out of room because I made too much space up there earlier. And you come up with two values. One is an x value of 5, and the other is an x value of negative 3. So you have two x-intercepts. One is at 5, 0, and another is at negative 3, 0. Those are the zeros of the function, which are also the x-intercepts. That's where you cross the x-axis. If you graph it, those 2 points are on the line specifically where it crosses the x-axis. Okay, so the next one is the same thing. What are the zeros? What are the x-intercepts? There's probably more than one. So if I take it out of function notation and I replace the y variable with 0 and solve for x, then the normal way of doing this is to factor it. So this would be a 2x and an x. Things that multiply to be 15 and then trial and error give you the negative 7 is going to be a 5 and a 3. And it's going to have to be a negative on the 5 and a positive on the 3. Some of you did factoring by grouping when you factored this kind of a trinomial. Various ways, various different methods of factoring. So then going back again to what they call the zero factor property, you set each of these factors equal to 0 and you solve for x. Now you have to remember, what in the world am I doing? I'm finding my x-intercepts. These are the x values of these two ordered pairs. One is going to be a negative 3/2, 0. and the other is a 5, 0 for that function. Okay, so that's how you find your x-intercepts given a function. All right, so now in the next set, you can see that they're going to give me the function already factored, which is really convenient. They're not going to always do this, but in this case, they have already factored the function for me. So they've already gone through the method which I just showed, and they factored this high-degreed polynomial. And they say determine the zeros. So remember, the zeros are those points where the y value is 0, and there's going to be more than one. So if I replace the y with 0, I have this statement. Someone who's already done the hard work and factored it for us. So now by the zero factor property, I set each factor equal to 0, including the 8x. So I set 8x equal to 0. I set x minus 1 equal to 0, and I set x plus 3 equal to 0. Now when 8x equals 0, you divide both sides by 8, and you just get x equal to 0, which is going to give me 0, 0 as my x-intercept, or the origin. This one's a positive 1, and this third one is a negative 3. So this one has 3 x-intercepts. The origin, the point 1, 0, and the point negative 3, 0 are your 3 x-intercepts. Now, this example didn't just ask me for the zeros or the x-intercepts, it also asked me for their multiplicities. Well, the multiplicity goes back to the exponent on the binomial right here. So, in this case, 8x was to the first power, so when I got the 0 of x equaling 0 from the 8x term, this point 1, 0, 0 is of multiplicity 1. The point 1, 0 came from the x minus 1 squared term, came from this binomial, and so it is of multiplicity 2. The negative 3, 0 came from this last term right here that I'm circling with my cursor, that little dot making circles. And so its exponent was a 3. This x-intercept is a multiplicity of 3. So you go back to your original function in factored form and look at the exponents, and that tells you the multiplicity. Okay, that tells you the multiplicity. So if that's a little bit confusing, let's do another one. Now let's take a look at this one to kind of get that a little more clear in our head. Okay, so to find the x-intercepts, you set the y value equal to 0, and you're going to get more than 1. So 0 equals 3x times x plus 1 to the 5th power times x minus 5 squared. Set each term equal to 0. Set the 3x equal to 0, the x plus 1 equal to 0, and the x minus 5 equal to 0. So I get an x value of 0, an x value of negative 1, and an x value of 5. I have 3 x-intercepts. One is the point 0, 0, one is the point 1, 0, and the third one is the point 5, 0. But they also want to know the multiplicity of each 0. The origin comes back to the 3x to the first power, so it is of multiplicity 1. The point 1, 0, what is its multiplicity? Multiplicity of 5. Very good. So you come back to its binomial, it's an exponent of 5. And the 5, 0 has a multiplicity of 2. Very good. Okay, there's your multiplicities. Your zeros and your multiplicities. So they have factored it for me. Okay, they have factored it for me, which is really nice. Okay, we're going to spend an entire section learning how to factor these things. Okay, so what is the deal with multiplicity? We've got that number. You taught me how to do it, and it's a done deal. But what does it mean? Well, when you have multiplicity, if you have an odd multiplicity, like a multiplicity of 1, or a multiplicity of 3, or a multiplicity of 5, or 7, if you have an x-intercept that has a multiplicity of 1, your graph will cross the x-axis, meaning it'll look something like this. It'll just cross the x-axis at its 0. Okay, nothing fancy. It's going to cross through it. But if you have an odd multiplicity greater than 1, like a multiplicity of 3 or a multiplicity of 5 or a multiplicity of 7, then this one is going to do what they call squiggle through the x-intercept. And it will come through the x-intercept like this. Okay, that is an image of squiggling through the x-intercept versus crossing. So if you're of odd multiplicity and it's a 1, you cross. Anything bigger than that is a squiggle through the x-intercept. Now, if you have even multiplicity, then you're going to touch or tap it. So this is what it means to either touch or tap it. You're going to come down and bounce off of it and go back. Okay, that's where you touched it at the x-intercept and bounce back off or tap back off. If your multiplicity is an even multiplicity. Weird stuff, right? Really weird stuff. Okay, so here we go. Let's go for it. Let's put together all the knowledge now that we have from this section and see if we can make something of it. All right, so it says determine the degree, the end behavior, find the x-intercepts and the multiplicity of each intercept, and then sketch the function. Okay, okay, so here we go. First thing, what is the degree of this polynomial? It's factored. A little more than 7. 8, okay, because there's a 1 on this x in the very front. So 5 and 2 and 1 is an 8th degree polynomial. Okay, it's a positive 8th degree polynomial. So what is its end behavior? Up, up. Very good. Y'all remember it well. Okay, so now let's find the 0. So to find the zeros, replace the y value, or the f of x, with 0. Then you set each of these terms equal to 0. So x is going to be equal to 0, x minus 1, and x plus 3. I'm going to get that hand to go away. Okay, so now we have x equaling 0, x equaling 1, and x equaling a negative 3. So these are the ordered pairs, 0, 0, 1, 0, and negative 3, 0. Those are the x-intercepts. Now we need to know the multiplicity of each one of these. What is the multiplicity of the origin as the x-intercept? 1. The multiplicity of 1, 0. And the multiplicity of negative 3, 0. Okay, so here we go. If your multiplicity is an odd number, specifically 1, we cross the x-axis at that x-intercept. If it's a multiplicity of 2, that was where we said we either tap or touch at the x-intercept. If it's a multiplicity of 5, y'all remember? That's where you squiggle through the x-intercept. Weird stuff. Okay, let's try to plot this. Let's get over here to this graph. So I have the origin, I have the point 1, 0, and I have the point negative 3, 0. My end behavior is up on the left side and also up on the right side. So at negative 3, I'm supposed to squiggle through. So I'm up. So I'm from the top, and I come through and I squiggle through it like that at negative 3. At the origin, I'm going to cross it. And then at 1, I just touch it and bounce off and go back up. So my end behavior is up, up.
That's cool.
Okay. It's pretty cool, actually. Okay. That's really pretty neat. Now, the one thing we don't know is we have no clue just how low this graph goes right here or how high. We don't know the vertical stretch. We're just kind of getting a general image of what it looks like. Okay? All right, so let's try another one. Okay, here's another example. The first thing we want to know is what is the degree of this polynomial? 9th degree polynomial. So what is its end behavior? Because it's a negative 9th degree polynomial.
Up, down.
Up, down. It's like a negative x cubed, right? It's like x cubed, but negative, meaning it's been reflected over the x-axis. Okay, so now we have to find the zeros. So I let 0 equal negative 3 times x minus 2 squared times x plus 4 to the 7th power. Okay, now the first one, when you set negative 3 equal to 0, that's kind of nonsense, okay? Because there's no x with the negative 3. If it was negative 3x, oh yeah, I've got a 0. But if there's no variable with it, it's not going to produce an x-intercept. So then I have x minus 2 equal to 0 and x plus 4 equal to 0. So I get a value of 2 and a value of negative 4. So I have 2 x-intercepts here. Okay, so my x-intercept at 2, 0, what is its multiplicity? 2. So if it's an even degreed multiplicity, does it cross, squiggle, or tap? Tap or touch, whatever, okay. What is my multiplicity at negative 4? 7. So it's an odd degree multiplicity, so it either crosses or squiggles. Which one? This is a squiggle. Okay, so let's try graphing it. So my end behavior is up on the left and then down on the right. I'm going through the point 2, 0 and negative 4, 0. Okay, so at negative 4, I'm squiggling through. So I'm up above, I'm coming down, and I'm squiggling through like that. And then at 2, I'm going to tap it and come back down. And there's a sketch of the graph. Okay, it's pretty amazing that it can be that simple. Okay, now that we're getting pretty good at it. All right. Okay, what is the degree of this polynomial? The next one down. 9th degree polynomial. So what is its end behavior? Down and up. So it's an odd degree and it's a positive odd degree polynomial. So to find my zeros or my x-intercepts, I replace the y value or the f of x with 0. A lot of multiplicities on this one. So now I get x equal to 0. I get x minus 5 equal to 0. And x plus 3 equal to 0. So I get a 5 and a negative 3. So I have the origin, the x-intercept of 5, 0, and the x-intercept of negative 3, 0. Okay, so what is the multiplicity of my 0 at the origin? Multiplicity of 3. What is the multiplicity of 5, 0? And the multiplicity of negative 3, 0. Here we go. Okay, cross, squiggle, or tap. Okay, the origin, is it cross, squiggle, or tap? It's a squiggle. Multiplicity of 4? Tap. All even multiplicity is to tap, and a multiplicity of 2 will therefore be to tap. Okay, to graph it, I'm going to be down on the left and up on the right. I'm going through the origin, the point 5, 0, and the point negative 3, 0. So my negative 3 is my first one I'm coming through. My negative 3 is to tap, so I'm coming up from below, and I'm going to tap it and come off of it. Then at the origin, I'm supposed to squiggle through. And then at 5, I'm supposed to tap it and come back off of it. There we go. Okay, I'm going to pause for a minute, and I want y'all to try part D. All right, so this degree is 2 plus 3 is 5 plus 4 is 9, so it's an odd degree polynomial, and it's negative. So it's like negative x cubed. So visualize negative x cubed, and the end behavior for the negative x cubed would be up and then down, right? Okay, so there's your end behavior. So now to get your x-intercepts, you set the y value equal to 0, which since it's in function notation, that is our f of x. Okay. Now you set each one of these terms equal to 0. So I get a 0, a 2, and a negative 5. Okay, so you've got to find multiplicity now in order to know the behavior at the zeros. So this is a multiplicity of 2, which means to tap, bounce off of it, touch one of those words. This is a multiplicity 3, which is to squiggle. And the negative 5 is a multiplicity 4, which is an even, which is back to tapping. So if your end behavior is up on the left and down on the right, I'm going through the origin, negative 5, 0, and 2, 0. Okay, so this arrow here says I'm coming down. I'm coming down. And at negative 5, I'm supposed to tap it. So I'm coming down. I'm tapping off of it. Then at the origin, I'm also tapping it. So I'm coming down and I'm tapping it again. And then at 2, I'm going to squiggle through, which is going to cause me then to go down, which is a correct end behavior. Oh my! Okay. It just takes a little practice, and we're not through. We're going to do some more, so that's not our last example. Okay, but it does take a little practice. Okay, so then they start talking about turning points, and they say the turning point is the point where the function changes from increasing to decreasing or decreasing to increasing. This is not difficult at all. So in other words, if my polynomial is going up, it's increasing, and then it changes and it's decreasing, then this point would be a turning point. Or if I'm decreasing and then I choose to turn and increase, then this would be another turning point. So where you change from increasing to decreasing or decreasing to increasing, those are called turning points. Okay, those are called turning points. Then it says the number of turning points is at most n minus 1 turning points when n is the degree of the polynomial. So don't make that hard. It's not hard. Okay, look at part A. This 5th degree polynomial, if it's a 5th degree polynomial, then they're saying that n is 5. So the maximum number of turning points would be 5 minus 1 would be 4. So it might have 4 turning points, it might have 2 turning points, okay? But it'd be a maximum of 4 turning points. 1 less than the degree. That's all there is to it, 1 less than the degree. The maximum number of turning points for this second example, you've got to first look at the degree. The degree is an 8th degree polynomial, which is what they call the letter n. So therefore, my maximum number of turning points would be what? 7. 1 less than the degree of the polynomial, or n minus 1 is the notation they use in all of their information boxes. Okay, so that tells you the maximum number, not the exact number, but the maximum number of turning points. Okay, so then in the book they go through this whole step-by-step process about graphing. They say find your end behavior, which is based on the degree. Find your y-intercept. Now that's something we've not been doing. Find your zeros, then sketch it. Now I'm not going to push step 5 or step 6, but you might see some of this in your homework, and it's based on symmetry. And you've already learned symmetry, and here's a little bit of information here typed for you if you see something like that in your homework. Meaning, does this thing show symmetry with respect to the y-axis? You know, that kind of helps you to graph it. All right, so let's focus on the new stuff. Let's go through the procedure. So step 1 was in behavior. Before I can get in behavior, we're going to go back and we must get the degree. What is the degree of this function in part A? 4th degree. It's a positive 4th degree polynomial. So what is its in behavior? Up, up. Okay, now here I've got to tell you before I forget. When you're doing your homework, if they give a lot of writing there other than just asking you what is the in behavior, it will say something like, what is the in behavior as x approaches negative infinity and as x approaches positive infinity? Okay, because you're looking to the far left of the graph and the far right. So if you see all that notation, don't worry about it. You know how to get in behavior, just answer the question. Okay, but you might see all of that typed in a really weird looking format, but that's all it is. So don't let that blow you away, because you know how to get in behavior. All right, so once we get in behavior, this set of questions says, what is the y-intercept before we get the zeros? I'm going to come way over here to the left side. Remember, your y-intercept is that point where the y value is 0, and you can only have one, because if there's more than one, it won't be a function, so there will only be one. Okay, one y-intercept. So if I let the y value be 0, let me take it out of function notation so maybe you can see this a little more clearly. Yep, your y, it would be, wait a second, I did that wrong, didn't I? Sorry, guys. Your x value is 0. Sorry about that. Okay, so then this is not hard. Just be careful with the negatives. So this is going to be 0 minus 1 squared, 0 plus 3, and 0 minus 4. So the only challenge here is all these exponents are going to come in here because of multiplicity. So this is negative 1 squared is a positive 1 times 3 times negative 4. So this becomes a negative 12. So your y-intercept is the point 0, negative 12. And this graph is pretty wild here. Oh my goodness. Let's don't look at this number. Okay, don't look at that. Okay, let's go by 5s. Let's say this is 5, 10, 15. So negative 12 would be about right here. Okay, let's go by 5s. So that would be about negative 12. Okay, so now let's go to what we've been doing and find the zeros of the polynomial or the x-intercepts. So I replace now the y value with 0. And then there's that thing called the zero factor property, which says set each one of these factors equal to 0, which will result in your x-intercepts. So I get an x equaling 1, an x equaling a negative 3, and an x equaling 4. So I have 3 zeros to this polynomial, or 3 x-intercepts. So to get the behavior of the x-intercepts, I look at the multiplicity. So my multiplicity of my x-intercept at 1, 0, this is a multiplicity 2. My negative 3 is a multiplicity 1. And my 4 is of a multiplicity of 1. Okay, so at 1, 0, do I cross, squiggle, or tap? Tap. At negative 3, 0, do I cross, squiggle, or tap? Cross. So multiplicity of 1 is always cross. Crossing without anything fancy happening when you cross it. Okay, so I have an x-intercept at 1, 0, an x-intercept at negative 3, 0, and an x-intercept at 4, 0. And my end behavior is up, up, and I have my y-intercept. Okay, so at negative 3, 0, I'm going to cross. So I'm not doing anything fancy, I'm just coming down. I really don't know how it looks when I go through the y-intercepts. You're just kind of guessing here, okay? But when I come back at the 1, I'm supposed to tap. So I'm going to say I'm going to come down a little lower, I'm going to come up, and I'm going to tap off at the point 1, 0. And then at the point 4, I just very simply go through that x-intercept. And there's a rough sketch of my graph, including my y-intercept now. Okay. All right. Here's another one. You're going to be pretty good at this long before you head home to do homework, okay, because we're doing a lot of examples. Okay, so before I can determine in behavior, I have to find out the degree of the polynomial. This is what degree? This is a third degree polynomial. So, and it's a negative third degree polynomial. So what is the in behavior? Up and then down. Okay, so now they are asking me for the y-intercept. So I'm going to come way to the left side. The y-intercept occurs when the x value is 0. So if I take it out of function notation, which I pretty much always tend to do this, and I replace every x value with 0, this will say y equals a negative in front of a 0 plus 1 and a 0 minus 3 squared. So this is a negative in front of a 1. Negative 3 squared is a positive 9. So this is ultimately a negative 9 value. So my y-intercept is 0, negative 9. Okay, and this graph isn't good either. Let's make this a 10 down here. Make these 10s. So 2, 4, 6, 8, 10 right here would be my y-intercept. 0, negative 9. Okay, so the y-intercept's not hard to find. You just have to be really careful with all the negatives in there. Okay, so now to find the zeros, I replace the y value with 0. So I have an x minus 1 equaling 0, and an x, oh, it's a plus 1, and an x minus 3 equaling 0. That negative in the front would be like saying negative 1 equals 0. Maybe I should do that. If I say negative 1 equals 0, that's a nonsense extraneous root is what they call that, because there's no variable with it. Okay, so if that negative out front is bothering you, that should fix the problem and let you know that that doesn't change anything as it pertains to your x-intercepts. So x is negative 1, x is 3. I have a 0 at negative 1, 0, and another at 3, 0. I have to go back to my multiplicity to talk about how the behavior of the x-intercept. So this would be a multiplicity of 1, and 3, 0 is a multiplicity of 2. A multiplicity of 1 is always what? Crossing. And an even multiplicity is always tapping. And they might call that touch, and they might call it bounce. Okay, those are a bunch of the words that they use. Okay, so negative 1, 0, 3, 0. My in behavior was up on the left and down on the right, and I've got that y-intercept way down there. Okay, so if I'm up on the left, I'm coming down, and at negative 1, I'm just going to cross. Then I got to come all the way down here and make certain I go through this y-intercept somehow. Okay, and then at 3, 0, I come back up and I tap it, bounce off of it, and there is a sketch of the graph. Is it starting to feel a little more comfortable? Getting closer to feeling good about it? Lots of little details to memorize. Okay, here's another one. Okay, sketch the function. It is a what degree? Third degree. And it is negative. So if it's a negative third degree polynomial, what is its in behavior? Up and down. Okay, I just use an EB. I don't know. I bet they're going to have the whole word in your homework. In behavior. So don't forget the EB means in behavior. Okay, so I need to find the y-intercept, which occurs when the x value is 0. So if I take it out of function notation, this would be y equaling a negative 3, a 0 plus 1 squared, and a 0 minus 2. So 1 squared is 1. So you got a negative 3 times 1 times negative 2, which is a positive 6. So you're going through the point 0, 6. Now what do I do? Okay, they're going by 5s. Okay, they're going by 5s on this table. So if this is 5, 6 would be about right here. Okay, there's my y-intercept. Okay, so my zeros occur when my y value is 0. So negative 3 equaling 0 is going to give me nothing. X plus 1 equaling 0, and x minus 2 equaling 0. Okay, so multiplicity is going to tell me the cross squiggle stuff. So I have a woo. Oh, that's above us. Okay, I thought they were beating on the board behind me. I was going to say something's kind of strange over there. Okay, a multiplicity of 2 and a multiplicity of 1. So a multiplicity of 2 is always to tap it, and multiplicity of 1 is always to cross. Okay, so here's my negative 1, 0. Here's my 2, 0. My end behavior is up and then down. So I'm coming down at negative 1. I'm supposed to tap it and come back up and off. I've got to cross that y-intercept, and then I'm going to cross it at 2 like that, and there is a sketch of the graph. Pretty nifty stuff. Okay, so intermediate value theorem. This is pretty cool. Now when we get to the intermediate value theorem, that's a lot of words, and so they call it the IVT, the intermediate value theorem. So it's not uncommon at all to call this the IVT. And here's this huge explanation. Let f be a polynomial function for a less than b. If f of a and f of b have opposite signs, then f has at least 1 0 in the interval. Okay, so the goal here is maybe algebraically we cannot come up with the value of the x-intercept. Maybe it's something really crazy. Like when we were doing the word problems and we were zooming in and zooming in, maybe we can't actually get the value of the x-intercept. But we want to know if one exists. So what they do is say, okay, well, if you have a point on your line and suppose it's at 3, 5, and then you have another point on your line and suppose it's at 6, negative 2. Given those 2 points, can I prove that there would be an x-intercept between them? Well, if the graph is, if I've got to connect the dots, right, if I have to connect the dots, then am I going to have to come through the x-axis? Yes, which would present an x-intercept. Even though I don't know what the value is of the x-intercept, if it's going to connect the dots, then I'm going to have an x-intercept. Okay, so here's the deal. If your y value is positive and then it changes to negative, won't you have to cross the x-axis when you connect the dots? Yeah. So if your y value changes sign from positive to negative or negative back to positive, you have to come through the x-axis. Okay? So in other words, they're talking about opposite signs on the y variable, which is your f of x information. So if your y value changes signs, then you have to be coming through the x-axis, meaning an x-intercept will exist. All right. So this interval notation here says, well, here's an x value of 3 and an x value of 6. So it's saying between 3 and 6, will there be an x-intercept, yes or no? That's what they're doing. Okay, so let's do a real example. So here's a function. You know, they're going to be much worse than this in a real world example. And so they're saying between an x value of negative 1 and an x value of 0, will this function cross the x-axis? I don't know where, but just yes or no, does it? So what I do is I evaluate it. So I have y equaling x cubed minus 13x squared plus 33x plus 35. If I plug in an x value of negative 1, okay, if x equals negative 1, then y will equal negative 1 cubed minus 13 times negative 1 squared plus 33 times negative 1 plus 35. This is going to be some weird number, right? what is this? This is negative 1. Negative 1 squared, so minus 13 times a positive 1 minus 33 plus 35. That's a negative 1 minus 13, which is a negative 14. A negative 14 minus 33 is a negative 47. And a negative 47 plus 35 is a positive 12. No, a negative 12, right? Did I do that right?
Why is the 33 negative?
Because it's 33 times negative 1.
Oh.
Did I do that right? Or pretty close? It's going to be negative. That's all we care. Okay. All we really care is this is a negative value. Okay, right? So it's under the x-axis. So this is the ordered pair, negative 1, negative 12. We are under the x-axis. Okay? So when x is 0, this should be easier. Okay? So this is 0 cubed minus 13 times 0 squared plus 33 times 0 plus 35. That's easy, right? That's a positive 35, which is a positive result, which is the ordered pair 0, 35. So my y value went from negative under the x-axis to positive, right? So if it's going from somewhere over here like negative 1, negative 12, up to a point 0, 35, would I have to cross the x-axis? Yes, I would. So the answer is yes, an x-intercept exists in there. In between those two x values, an x-intercept will exist. It will cross the x-axis. I don't know exactly where, but it's going to come through it. That's all I want to know. Yes or no, will one be in there? Okay, and then one more like that, and it'll be the end of this section. Okay, a lot of details in this section. So here we go. Remember, this is an interval. This is not an ordered pair. So it's saying when x is negative 3, and then when x is negative 2. So between those two x values, will the graph cross the x-axis? Okay, so when x equals negative 2, y will be 4 times negative 2 cubed minus 8 times negative 2 squared minus 25 times negative 2 plus 50. I should have started with negative 3. Whatever. Okay. So this would be 4 times negative 8, which is a negative 32, minus 8 times a positive 4 plus 50 plus 50. Ugh. So this is a negative 32 minus 32 plus 50 plus 50. So that's a negative 64 plus 50, which is a negative 14. Negative 14 plus 50 is a positive 36, right? So all I want to know is this is a positive result. Did I do that right? Okay. All right. So if x equals negative 3, and I should have done this one first, but whatever, okay, then y would be, oh, this is going to be really bad. These are like big numbers. Like, I might have to pull my calculator out now. Or get y'all to pull yours out, right? Okay, negative 3 cubed is a negative 27. And negative 27 times 4 is something big. I can't do that in my head. Should have done this. I have to cheat and tell you guys. Okay, so what do I have? I have 4 times a negative 27, which is a negative 108. And then negative 3 squared is 9. 25 times 3 is 75. Okay, so now I have a negative 108 minus 72 plus 75 plus 50. So a negative 108 minus 72 plus 75 plus 50, and I get a negative 55, which is a negative result. So it changed, the y value changed signs. We were going through the point -3, -55, and then the point, or then first the point, no, then the point. Okay, so if I go through those 2 points and I draw a line, am I going to cross the x-axis? Yes. So the answer is yes, and x-intercept exists in that interval because the y value changed signs. Because y changed signs. Signs meaning negative to positive or positive to negative. Okay? That should finally end this long section.